Sound is produced when something vibrates. The vibrating body causes the medium around it to vibrate as well. The wavelength and the speed of the wave determine the pitch or frequency of the sound. Sound equals frequency times wavelength. Sound travels at a constant speed at standard temperature and pressure, STP. Thus, frequency is determined by wavelength. The longer the wavelength, the lower the pitch. The height of the wave is its amplitude. The amplitude determines how loud a sound will be. Greater amplitude means the sound will be louder. With sound. Sound is produced by pressing down a key. When the key is pressed down, the damper is raised. The function of the damper is to stop the vibration of the string when the piano player wants to stop the sound. When the key is raised, the damper falls back against the strings. Simultaneously, when the damper is raised, the hammer hits the string. It exerts a large amount of force in a short amount of time. This relates to the physics concept of momentum. Momentum can be defined as mass in motion. All objects have mass, so if an object is moving, then it has momentum. Momentum is transferred by impulse, which is force that is exerted in a certain amount of time. Impulse is really just change in momentum. Change in momentum, or impulse, is equal to force times time. Therefore, increasing force and decreasing time regarding a piano increases the impulse. The force of the hammer depends on how hard your finger strikes the key. This can be related to the physics concept of kinetic energy. Kinetic energy is 1/2 mv squared. The main source of energy that the hammer carries is the kinetic energy when it is being thrown or activated. Since the mass of each hammer is constant here, we are not interested in it. We are only interested in the velocity, which is the speed of the hammer hitting the string. The kinetic energy changes with the square of V. That means a slight change in the V will result in a larger change in the volume of the sound, thus the tone quality. The vibrating piano strings themselves are not very loud, but their vibrations are transmitted to a large soundboard that moves air and then converts the energy to sound. The strings of a piano which vibrate are made of steel wire and are all of different lengths and diameters. When the length of the string is doubled, the pitch lowers by 1 octave. The strings are not the same diameter. That is because the strings creating lower sounds would have longer string lengths and higher sounds. They would have to be very, very long in comparison to the short strings. Instead, the strings are usually different diameters in order to fit all the strings in a house-friendly piano. The highest treble strings have thinnest diameters, usually around 0.7 millimeters thick. Then, as the strings gradually increase in diameter and length, the pitch gradually decreases. Near the middle, the diameter is 1.4 millimeters thick. However, soon after the middle C, the thickness of the wire makes it too stiff to vibrate properly. Now these wires are made of regular steel wire which is wound up in a copper coil. This copper wire adds mass. Shorter strings are less resonant than longer strings. Union strings, 2 or 3 strings tuned to the same pitch, like this cluster here, are what help to achieve a louder sound from the shorter treble range strings. Treble pitches have 3 unison strings. Tenor pitches have 2, bass strings only have 1. There are 88 notes and as many as 236 strings. There's also the matter of tuning the piano. A piano sounds best in tune when its octaves are stretched to match the inharmonicity of the strings' overtones. Most notes of the piano have 3 corresponding strings. A piano sounds best in tune when these strings are slightly out of tune with each other. This deliberate mistuning allows the vibrations of the strings to last longer. We can also talk about the physics concept of frequency, which refers to the rate at which the volume is heard to be oscillating from high to low volume. A piano tuner frequently utilizes this phenomenon of beats to tune a piano string. If we pluck a string and tap a tuning fork at the same time, and their beat frequencies are not identical, we need to adjust the tension of the piano string. We do not want to hear the beats, since as the piano string becomes more in tune with the tuning fork, the beat frequency will be reduced and approach 0 Hz. A piano usually has 2 or 3 foot-operated pedals. The rightmost pedal raises the dampers on all strings so that they continue to vibrate after a key is released. And are also free to vibrate when other notes are played. The leftmost pedal makes the instrument quieter by either shifting the hammers to miss one string or else by moving the hammers closer to the strings. The center pedal, if present, usually sustains only those notes being played. This is the day you will always remember as the day that you learned the physics of the piano.
Alas, my children, this is the day you shall always remember as the day that you all know. Captain Jack Sparrow.